Hi, so it's Marie Diener-West, and I'd like to walk you through a demonstration of using Stata for both simple logistic regression and multiple logistic regression. So I will open up a data set right now. If we inspect the variables on the right-hand side, we'll see that we have vitamin A status, 1 for vitamin A, 0 for placebo, case status, which is 1 for death, 0 for alive. We also have gender, which is 1 for girls and 0 for boys. And so if I was interested in first tabulating the relationship between vitamin A and case status, I could use a case control command to look at case status, meaning vital status, versus vitamin A. By using the case control command, I can see the number of cases, which would be those that were exposed to vitamin A. So the cases are actually the 120 that died. The controls are the 120 who survived. 46 of those who died had been exposed to vitamin A. 74 had not. And of those who remained alive, 61 had been exposed to vitamin A and 59 had not, had received placebo. So what we see here, though, is that the estimated odds ratio of death in the vitamin A versus placebo group is 0.6. The 95% confidence interval overlaps the value of 1, which would suggest no difference in the odds of death between the two treatment groups. And we see as well the chi-square p-value, which is greater than 0.05. It's 0.0514. So after that, we might perform a simple logistic regression, and I could use the logit command, followed by case, followed by vitamin A. And we see that now we have a simple logistic regression in which we're modeling the log odds of vital status or case, log odds of death as a function of vitamin A. We see here that our model would be beta naught plus beta 1 times vitamin A. The estimated coefficients that I'm pointing to are for vitamin A. This is B1. It's a log odds ratio of death in the vitamin A versus placebo group. And then the constant is the intercept. It is the log odds of death in the placebo group. So those coefficients are on the log scale. But if we were to test the null hypothesis that beta 1 equals 0, we would look at the p-value, which is not statistically significant. We would also look at the 95% confidence interval, and we see that it overlaps the hypothesized value of 0, again, suggesting a non-statistically significant relationship between treatment and vital status. I could change this by, instead of using the command logit, we could use logistic. And by using logistic, we no longer see the column labeled as coefficient, but rather it's now exponentiated, so that the vitamin A coefficient is exponentiated to form the odds ratio of 0.6. We again see the p-value of 0.05. We also see the confidence interval overlaps the value of 1. So again, suggesting no statistically significant relationship between treatment and vital status. Now, we also could perform this same step of logit, case, and then gender to allow us to look at the relationship between mortality and gender. Here, our model is the log odds of death is a straight line relationship, beta naught plus beta 1 times gender. The coefficients are estimated here. So B1 is now the coefficient for gender. So it's the log odds ratio of death in girls, the group coded 1, compared to boys, the group coded 0. We see the p-value is large, 0.115, and there's a confidence interval that's wide and overlaps 0. So there's no statistically significant association between death and gender. We can also use the logistic command, and I'll change and put the covariate of gender here. And we would see that now the column is labeled odds ratio. The gender coefficient is exponentiated to form an odds ratio of 1.52, but you'll note the p-value is the same, 0.115, and the confidence interval is wide and overlaps the value of 1. Now, we can also perform a multiple logistic regression by adding in both covariates, and it doesn't matter which order they're entered, but I'll order vitamin A first and gender next. And now we see that our model has 2 covariates. The model is the log odds of death equals beta naught plus beta 1 vitamin A plus beta 2 gender. And I used the logistic command, so we already have exponentiated the coefficients. We can interpret 0.63 as the odds of death in the vitamin A compared to the placebo group, controlling or adjusting for gender. It's not statistically significant as evidenced by the p-value and the 95% confidence interval overlapping 1. We could also look at the exponentiated coefficient for gender, which gives us an odds ratio of 1.41. It is also not statistically significantly associated with death because the p-value is 0.200 and the confidence interval is wide, overlapping 1. So if we wish to do some model selection, we could use a different command, and that is the GLM command, in which we would follow it by the Y variable, which is case, followed by the covariate of vitamin A. And I could indicate that the family is the binomial, so the outcome is modeled or expressed by a binomial distribution. And the link between the expected value of the outcome and the straight line relationship with the covariates is given by the logit, which is the log odds. So I see, again, a familiar coefficient of negative 0.509 for the log odds ratio, but I'm going to estimate the statistics from this regression and store it in a place called A for model A. I could run the same command using gender instead of vitamin A, and I would see the same coefficient that we got with the logit command, the same p-value, same confidence interval. I'm going to now store that in a location called B. And then we'll do one more. We'll look at a multiple linear regression in which we are regressing the case status or dead or alive on the 2 covariates of vitamin A and gender. And we see here the coefficients that we received for vitamin A and gender before, the associated p-values and confidence intervals. And I'm going to save this in a place called C. So now there is a form, it's a pseudo form of cross-validation, which aids us in model selection because it balances the log likelihood from the model along with the number of parameters that are estimated in the model. And that value is called the AIC, or Ake-Ike information criterion. So I can estimate the AIC by following in the command stats space with an asterisk. And then I can see the Ake-Ike information criterion is given here. It's in the second to last column. And our guideline is to choose or select the model that has the lowest AIC. So you can see these AIC values are very similar. But if we wish to choose one model, the lowest one would be model A, which includes only vitamin A status. But they're really quite similar. We saw that they actually had non-significant associations. And so, in fact, I could do one more thing. I could estimate the log odds of death without any covariates in the model. This has no covariates. I can see that this is estimating the coefficient as 0. I'll estimate this and store it in another location D. And now if I use the estimate stats command, we can see that actually the model D that has no covariates doesn't perform very differently from the other 3 models. So in fact, all 4 of these models are roughly equivalent in terms of not showing a preference for one model over the other. So that is one investigation we could do by model comparison. We also could rerun model A, since that may be the one we would choose because of the lowest AIC. And afterwards, we could conduct the Hosmer-Lemeshow goodness of fit test. So I would say ESTAT, GOF, goodness of fit. And we'll try that one more time. And I'm not getting a valid response here. So let's see if I say estimate goodness of fit, it's still not helping. But this is where I would go to the help menu. I would look for the command ESTAT goodness of fit. We are performing a logistic regression, but we see that this is not valid with the GLM command. So this was something good to learn. So what we could do is repeat our logistic regression of case status onto vitamin A. And then after that, estimate using ESTAT goodness of fit. And we now see that we are running the right command for this logistic regression to test the goodness of fit test using the Hosmer-Lemeshow test. We can see that we have a resulting chi-squared statistic of 0, and we have a probability of that's missing. So this can be the case where there's actually not a good solution for this. We'd really want to investigate models that possibly have more variables than vitamin A and gender, and see if there are other variables that help explain mortality at 6 months or the odds of mortality at 12 months. So we'll stop for now, but if you did want to save this as a do file, we could delete the red commands, which were errors. We could highlight all of the commands we just used and send it to a do file. So that do file is behind my screen now, but we could save that and we could run this again in the future. So with that, I'll conclude. Thank you for your attention.